大家好，我是王博老说半岛。Hi folks, today we're going to continue the discussion about the backside PDN and with a focus on which etch stop layer is best for you. I'm talking about the one proposed by IMEC and then TSMC and Intel. We do not know exactly which etch stop layer they use, but so I just lay out what are the two possibilities for you to review based on IMEC's proposal. All right. And as an icebreaker, today I'd like to mention that TSMC Fab 6 in June this year has been ready for business. They provide 3D fabric with SO, IC, info, CoWoS, all these and advanced testing. And they're trying to make the world's largest packaging facilities, especially for advanced one, right? The less advanced one, they are not that into the market, but the advanced one definitely, all right. With all these very advanced one, we're especially using what we mentioned before, the hybrid bonding interconnect with the copper direct bonding. Those are, I think they master the art of it. Talking about the backside PDN, my personal assessment is not, I think everybody has their own strategy based on the product they are targeting. It's not everyone use the same approach. And if you look at what I mentioned before about the power improvement, this is very critical for chips with very power hungry. They consume a lot of power. Then you like to reduce the power consumption by reduce the resistance to the transistor. So you move your connection from the front side to the back side with the power rail and all that improvement. That is one thing. That's one very powerful feature for the backside PDN. But there's another big win for backside PDN is that you remove the routing from the M1. M1 is the worst routing area that you can think of. And with the backside PDN, actually, you relieve tremendously the M1 routing congestion. And what happened is that the SRAM scaling, right, continues. We've been trying to try to find some SRAM, try to reduce this 6 transistor, right? They all tied up together to make an inverter. And that SRAM configuration, we spent 20 years trying to make, say, one transistor, one resistor, some kind of one T1R approach, or replace it with something else. None of them is successful. I think we'll kind of give it up already. And nobody can compete directly with SRAM in terms of the 6 transistor design because you really occupy a big area. So anything to relieve the congestion, especially the M1, done by the backside PDN is a welcome news for the SRAM scaling. Without it, it's very difficult to scale. It got transistors all tied up together. And you look at in reality, exactly when TSMC going to introduce backside PDN, it looked like from what is announced that it would do it after N2 mature. So the first generation N2 is the nanosheet gate all around a structure, the 3 nanosheets forming a transistor that will not have backside PDN. We will discuss why that's the case. My personal assessment is that because it's really difficult to make it successful. HBM process readiness is not yet there. And the process concern is quite a few there. And Intel did demo. They demo successfully backside PDN using Intel 4 nanometer process. And they claim they did they claim they don't see too much of a problem. Okay, that's good. That's very good news. I hope that's the case in HVM later on in the high volume manufacturing. They really see the benefit. and then they really can mature in a way that HBN is ready. It's really good news. Right? The competition is very fierce, and that is good news for everybody. Samsung is a little bit behind, and they may catch up later. They're still a powerhouse in manufacturing as well. So let's go back to our topic. Which etch stop layer is best for you? So today's focus is etch stop layer. All right. So what are the etch stop layers? If you look at the simple graph of the any chip, current modern chip, this is what you're gonna see. The mini metal layer. See that? There's the green line here, and a lot of them are dielectric capping layer and etch stop layer, because you can obviously see they are trying to pattern something, and then once they pattern it, the rest is the via or the copper wire. They're going to put it on. So a stop layer is something to stop on, right? It used to define is a layer used to define the microstructure thickness by stopping the etch at this layer. So that's what it's for. Stop something, all right? Stop something means that this is different from the environment. So here you could have many options. You could use oxide, carbide, nitride, metal nitride, etc. So many material other than silicone or something that is that you want to etch through, right? Here is IOD. So it was something different from the IOD layer. So it come to mind would be, say, silicon carbon nitride, something different, right? You cannot have the same material, gotta be different. Then today our focus will be a strange one, a special one, silicon germanium against silicon. That's what our stop layer is about in this talk. And we'd like to introduce a concept called selectivity. Selectivity means that the etch rate of a material to be etched versus not to be etched. So how good is it? Say selectivity, say SiGe against silicon. You mean that you put usually a dry etch, or could be a wet etch, but usually it's a dry etch. And you etch something through it, and you will stop a certain layer. And what you hope is that the etch rate of the material not to be etched has to be very small. The etch rate would be very, very small. And then the one you're going to etch through is very large. And that is selectivity is a ratio that is, as high as possible, I suppose. Okay. Before I go into our focus, let's review some of the world famous stop layers. There are many stop layers, as I mentioned before, but there's one that in current node, like 3 nanometer, 5 nanometer, the most important stop layer is inside the self-aligned contact. This self-aligned contact is very critical. It's what Intel introduced in 22, the first generation of FinFET. And nobody do 22 now, right? Everybody go to FinFET directly at 16 or 14. And you can see this, the simple flow is like this. So this is a gate process. You define a gate. And then you recess the gate a little bit. And you put a stop layer here. This is the layer you're going to put it on. And then you have an etch contact here. And then this is what your future will look like. Look at this. Okay. This is future, you will put a contact on. And here you can see that this is a stop here that you want to avoid the contact to touch the gate. So the critical part of this process is obviously, all right, without this gate contact, when you etch it, wow, you're going to hurt your gate. And that's no, right? Gate is the most important material you're going to use to control your work function. Without a proper control work function, your device is dead. Even you could say my device can have very high drive current. It does not matter if you cannot have control VT. There's no device to be discussed. Okay, so the etch here Yeah, you will try to protect the gate is critical. You put something to stop it, and that is your stop layer right here. It's one of the most famous one in the world right now. It's one of the most difficult one. Okay, and and then last year the IDM TSMC published a paper on this subject. All right, so the TSMC 3 nanometer self-aligned contact, and this is the one I would say the key enablers propel TSMC to be number one by perfecting this critical stop layer, which they call it harm mask. It's something to stop upon. So it can be a harm mask, doesn't matter. You look at it. So the etch loss. So he's talking about how fine how fine the control should be in order to make things work. Before going to that deep, let's look at the traditional contact. All right, you have you want to contact here, so it's a drain here, and then the traditional one, just put it is very close. All right, and then that's what you hope for. But there's a gate to contact to gate isolation, as we mentioned here. If you have something going on here that you're not protected, then your etch or your deposit gonna interact with the gate metal here, then you're doomed. So there's nothing you should have. You cannot have any reaction here at the tip of the contact gate. So what I did is put a harmax to protect it, 10 nitride, okay, or some kind of nitride, as long as you could put it inside. Nobody exactly know what is the material TSMC put here. I think they probably work with the TEL or LAM or applied material to deposit the hard mask. And the key is to make it rectangular, okay, versus a round one. This minute difference is enough to change the C effective, the capacitance in this structure, right? And then so here is no, and here is still vertical, meaning that the edge did not hurt it, all right? Their selectivity is very high here. See, the mask loss after edge is less than 0.2 nanometer. That's how good they can control, meaning that the edge chemistry did not hurt it at all. Just give you a perspective. This is 2 angstrom. An atom is about 3 angstrom. All right. And this is less than 1 atom. So it's nothing lost here. But if you have the regular one, I mean the previous generation one, I think this is their PR process. You can obviously see it does not hold the rectangular structure here, like here. Here is not rectangular anymore, and then it lost 5 nanometer. That will enough to um, to hurt the device. So that's how critical this stop layer is. All right, and TSMC obviously they just announced the success. It's just celebrate the success of 3 nanometer because iPhone 15 Pro using the 3 nanometer chip, and that's a big success, as you know, right? Then, so this is the world most famous stop layer. Currently, only in TSMC can do this. Not Samsung, not Intel is able to do the self-aligned contact with such a fine control. So look at these numbers, just amazing, right? You're controlling within 1 atom, and that's why TSMC is so successful these days. And let's go back to IMEC's proposal. I have introduced this figure from IMEC, the paper they provided. And then they said they want to create this pattern. They have all these nano TSV, battery power, backside interconnect. All these are based on the so-called SiGe stop layer. It's a sacrificial one. So this you cannot see it now. So this is a device they build upon, right? It's a 4-pin device. It cannot be seen after process. All right. So that keep in mind. And let's review its flow a little bit. You can see that the silicon, this is the bulk substrate. They bought it from MEMC or somebody, right? Now they're going to do a epi SiGe, and that's your stop layer. And then so you grow this, and then you grow silicon on top of it. So that's an epi done by probably an ASML. And ASML is pretty good at doing this, right? And then you have a well, and then film patterning. And we can talk about this later. All these are prop, and then the low temperature HDI. And it is on this silicon layer that start to build the devices with the barrier power rail, the buried power rail, right? And then they build up to M1 because that's all they need to demonstrate whether this process is working or not. IME does not care about whether it's going to work in high volume manufacturing. It's just they are trying to say that this process, a simple process, until M1, it worked. The rest is your job to make it perfection. My job is pretty much sell this idea to my members, Intel, Samsung, TSMC are all key members of IMEC. So IMEC is very good in generating ideas and using their 300 millimeter FET on their FET on SiGe, they could demonstrate that hey, this is my flow and it worked. And then it did what I tried to demonstrate. And take the lesson. I have some IP for you. You could use it freely. So all that 9 yard is what I make good at, right? And then the member companies like TSMC, Samsung, and Intel would take this and then try to develop their own version, of course. They're not going to copy exactly, right? But so we're not going to go to detail about what's going to do. I'm going to focus on the SiGe, uh, SiGe here, SiGe stop layer, and some other stuff as well. And then they're going to flip it and bond it, right? So the low temperature, everything's low temperature, all right? It's not good news, actually. I explained to you why. Right? All this temperature, they are all going to low temperature. And that is a concern to me. And then they actually removal, right? Here's the removal. And then that's what happened afterwards. So this flow eventually had two wafer bound together. Okay. So now let's look at, since we're going to talk about using SiGe as the stop layer, why I say here is not ready for high volume manufacturing. What do I mean by that? All right. Let's go one step at a time. Before we go into SiGe, at the end of the day, we're going to etch it. So we're talking about etch selectivity against silicon informing nanosheet. And there are two versions of it. One is to etch this and then not etching silicon, or etching silicon, not etching SiGe. Here, the first example is etch silicon germanium, SiGe, not etching silicon. And this has been used for the nanosheet structure, right? This is what we saw regularly. The devices, they put SiGe, silicon, SiGe, silicon, SiGe, silicon. This is the nanosheet structure that everybody saw on the news. And everybody had own way of doing it. But after you're forming it, you want to create something, a pouch that etched in for the inner spacer. All right, here is for the inner spacer. The SiGe here is for later IMG process. And then you want to have a rectangular square profile. You don't want to have this rounded shape, all right? That's what you don't want. You have a very sharp silicone, the corners. That's what you desire for. The wet edge won't give you that. Wet edge is not going to give you that. It's a rounded one. The dry edge, yes. If you do the right good job, you should have it. So they calculated this selectivity. Okay, it can be very high. And here, but it still has a little bit. You see that? It's still, to some extent, still a rounded shape. It's just better than the wet edge. It's very round. And at the same time, you can see that the silicone is a little bit lost. You have a silicone loss. And that is not good either. because silicon is only about 5 to 6 nanometer. You don't want to have too thick, then the device cannot control. You're going to have too thin. If too thin, the VT cannot control. And anything like under 4 nanometer, you cannot control it. And then over 6 or 7 nanometers is kind of useless. So you're controlling like 5 or 6 nanometer, all right, for each layer. And this is not an easy thing to do. But of course, people done it. So this is no problem already. So people spend years, especially the TEL did a pretty good job here. Or LAM, they have very high selectivity. I saw selectivity up to a couple hundred exist. All right. But what about the other way around? Here we want to etch silicon. So if in the future you want to etch silicon and then stop here and stop layer here, what do we what do we want to do? If we need to do that to start and stop layer, all right? What do we need to do? Well, can we have infinite S selectivity of SiGe against silicon? Well, yes, it's been done in 2000, I think 2010 or 16, I forgot, on this book. There's a process that using this chemistry, CS4, CS2F2, N2O2, a high pressure. So silicon etch rate is very high, while the SiGe etch rate is almost zero. So they form this very clean shape. So here you etch silicon and leaving SiGe behind. There's no touch. So you can imagine that people can perfect this recipe or similar recipe that we can enable SiGe as a good stop layer against silicon for backside PDN. Right. All right. So technically, yes, you could use SiGe as a stop layer. The etch chemistry is there if you need it. All right. And then no problem. All right. So what the concern? But there are other concerns. What are the concerns? Okay. My concerns are as follows. That the concern one, channel, see, this is a channel, right? You're building channel using the silicon you grown epitaxially from the chamber that you put the SiGe, and you put a SiGe together. So like that is, right? This is what it says here, right? At first you can take the dope and then you epi it. So your silicon channel is formed inside continuously with the SiGe together. Is that a problem? Maybe, yes or no. You see, the chamber that you use to grow SiGe may have different oxygens, and you don't want oxygens because high oxygen will lower your carrier mobility. It's a contamination. You need to have very stringent oxygen control. And the wafer you bought from MEMC or somebody else or SEH, their oxygen level, the silicon inside is very, very low. And here in your epi tool, it's not that low, to be frank. They try to make it low, but it's not that easy. It's still higher than the silicon you bought from the MEMC or SEH, the wafer you bought, incoming wafers, because they have a much stringent oxygen contamination control. All right. And your chamber is just your chamber. Sometimes it's not that easy. All right. And then the incoming wafer, they check the oxygen level, regularly, and they to ensure they have a very good quality silicon. So you will buy them. And it's not impossible to control. You can see that people try to use the Paul company who sell these point use filter, point use purifier, Comexi gas clean. They will use palladium or something special, catalytic matter metal to extract the oxygen out. Okay, and then it's because that the oxygen in the film, they have very undesirable effect on device performance. It will increase the mobile charge. Okay, it will shift the breakdown voltage and then increase the leakage current. So oxygen in the film is the one you need to be very careful with. Very careful with. So you put some filters on and try to say, okay, my incoming has some hydrogen line purified. But don't forget, your chamber need to be clean too. It's just not incoming. You just clean the hydrogen line, yeah. But there are other gas you're using, right? You have silane, which, of course, you're not going to put a purifier, but chamber itself is kind of dirty to some extent. You try to make it as clean as possible, yeah. So that's why you're going to change your PM frequency to make sure that's clean. And people study that, right? It has that it's an Asm Epsilon, this old tool. The new tool is the same. They have the palladium purifier that will capture the oxygen to the PPT level. Pretty good. That's a parts per trillion. It's a very nice number. But it's still sometimes you need to be watch out that your oxygen concentration in your epi, in a silicon epitaxial layer, could go as high as 10 to 21%, 10 to 20 E20, E21 centimeter cube. This is pretty high. This is like 1% of the atomic density, and that is not good, right? That's not good. So you see, oxygen higher than this, then that will give you the device problem. So the HVN per se, they have to manufacture their own chamber channel right now, which is kind of a hassle. Incoming with a very high quality, it turns out you cannot use it. You have to grow your own. And the chamber you grow on is, say, 600 to 700 degrees Celsius. It's very hard to keep it clean. That's the problem, all right? So that's why I mentioned the concern one. The channel are from silicon grown from SiGe, a non-POR process. This is a fundamental shift. Versus baseline. The baseline is that the silicon channel is obtained from the high quality incoming wafer you bought from the big suppliers. They are very high quality, very low oxygen contamination. They're monitoring all the time. And for you to do the same thing, you don't have the right equipment, you don't have the right temperature, and then so that kind of be difficult. Right? Kind of difficult. It's not impossible, but you need really really a big homework for the fab to check into it. All right. And so that's one. That's one thing. Then the concern two, you mentioned the low TSDI here. So once you got the channel and you start to build your device on top here, right? And the first thing you do, you need to build the HDI, of course, shallow trench isolation. But you cannot do it high temperature. You have to do it low temperature. All right. So we will later explain why here. Okay. Because you want to avoid free SDI. And void free SDI by usually by HTP-CVD, they require very high temperature. Why? Because you got liner there, right? You got liner there, you have to do the liner first, and then the liner and neo, they are all high temperature. And so what's the problem with high temperature? So it's okay, you need high temperature, just do high temperature. Well, it turns out you cannot do that to higher temperature because germanium will diffuse out of the SiGe layer. Well, why is that? Okay. It's because the germanium interdiffusivity value are getting serious, right? This number getting serious to this level, all right? When your temperature is 8 to 900 or higher. And so these actually will give you problems. Germanium interdiffusion at high T can be very significant. And why is that? The reason is that germanium the melting temperature is quite low. It's about close to 500 degrees lower than silicon. Silicon is 1414 Celsius. And then germanium at 938, close to 940 Celsius. It's almost 500 degrees lower. This means that germanium has a lower temperature, can move around freely at high temperature. See here, in 900, you can imagine that the alloy inside is going to be a liquid. It depends upon your germanium content. So it's very tricky to avoid this problem. You need to lower the temperature. You cannot have too high temperature. And that's the reason, right? You said low T. or low T. But low T, you bump into a problem that you need void-free SDI. The void-free SDI is that because SDI right now has a very high aspect ratio. This aspect ratio, this is just a simple one. The current one is even higher. The aspect ratio is so high. And then you want to have complete void-free process to fit it nicely. Sometimes you cannot, you see. This aspect ratio obviously is higher than this one, right? Because this is wider and this is narrower, right? Aspect ratio is the height divided by the width of the hole, by the diameter of the hole. And this one is higher, and you can see that there's a big void here. The big void here, there's tons of trouble. Imagine if you CMP here, then the hole open, you got all the dirty things coming in. Or even the dirty things that are coming in, the oxide here is weak. Then you might have reliability issues. So this is the problem. To solve this problem, if you do low temperature and then say even to LD process, you can fit it up. But what's wrong with the low temperature process? More than one can be void-free, but the oxide quality is not good. And because when you form an SDI, which is SiO2, all right, the SiO2 need to be very high quality. How do you make it high quality? You need to be annealing very high temperature. If you don't do it, it look good right now. I say, okay, this is good. But later on, have a process, this become weak later. So it can be void-free. It's okay initially, no void-free, but later on you develop problem. So the low T SDI could give you some headaches. So that's one I put it a concern too. SDI may have gap fill issue, may or may not have gap fill issue, but will have the reliability issue. So all these are problems that you need to be worried about. Okay. Now the concern 3. Device channel growth upon silicon is a metastable region. So okay, I solved my oxygen problem. So what's the problem now? Well, there are still problems. Even you solve the oxygen contamination issue here. You grow a very nice silicon, the layer on top of SiGe, but are you worry-free now? Well, I'm not sure. Look at this. How thick you need to grow? Say, in here, the whole stack, all the way here, see, including this SDI, this could run you close to 100 nanometer, sometimes even higher, right? So this thickness is very thick. And then how thick can grow before it become problems? If you look at the, what I meant is that why it's called a metastable region. A metastable region is the epitaxial growth that if you hit the black line here, it will relax with dislocation. For example, if you have 40% germanium and then you grow 100 nanometer, then the epitaxial quality will be bad. You will be full of dislocations. But if you grow only the say 5 nanometer, you're fine. No matter what you do, it's very stable. But unfortunately, you need very thick one, right? You need some 100 nanometer. And then what's the range of germanium? Probably in the 20 to 30%. Okay, so you are fine. You are okay. But this region, why is called metastable? Well, because it is not stable. It is not relaxed. It's right in between. And the right in between is not a good thing because it will relax and form in this location when you experience very high temperature anneal because you want to go to relax. All material that in metastable region are not stable as you think, and you will go into a relax mode. You like to relax, all right? Then that's the nature of the layer. It's just like to relax. And then if you give a chance by doing what? By giving a very high temperature anneal, okay? And then so you're going to have a problem. In contrast, channel obtained directly from the silicon wafer, but right, you buy from the wafer, you don't have that problem, right? It does not have the above concern. If you could have that layer um, directly put it home, we don't need uh, you don't need to have this SiGe. You could use SOI. You don't have a problem. Okay, we'll talk about that later. Okay. And why is that? If you look at this picture, there are two pictures here. This is SiGe, right? This is not exactly the same example I mentioned. It's SiGe grown on top of silicon. I'm just using as the demo that initially does not have the dislocation much. Oh, yes, some here, but let's ignore that for now. And then during a high temperature anneal, this is after implant, and then anneal, you can see tons of dislocation popped up. All right, so this is bad. And then we have do we have that the similar process? Yeah, we do. We have the NP anneal well. We have a well, that's the implant. Okay, and then we're gonna anneal back. So it does have this, and even at this step, the high temperature anneal already. Not to mention later on, you have a lot of high temperature anneal. Especially the RMG process, right? The SD is pretty high as well. I see this is RTA here. So this is the dopant activation temperature. This is pretty high, okay, and in a very long time. So all these are concerns, and so it will relax if you give it a chance. So you need to be very careful. So you cannot trust yourself that I just initially is very nice and it will stay that way. Oh, that's not true, because it may not stay that way if your process is not tuned, readjusted to reflect that you need to protect this layer. Okay. Okay, that's what I meant by concern 3. The channel grown on silicon germanium is in a metastable region. It could be unstable and turn to relaxed and generate tons of dislocation if you're not careful with your high temperature need. Okay. Then the concern 4 is that silicon germanium is an SRB, it's a stress release buffer or strain relax buffer. Okay, it is a stress. It's a SRB is a strain relax buffer that is 7 nanometer. A lot of people try to introduce that for the 7 nanometer node, such as Samsung and IBM. So they use a silicon germanium buffer, and then on top of that grow a nice channel. And this is similar to what we saw here, just not that complex. This is very simple, our CT1 layer. And their stress relief buffer is very complex. But it does not matter. From that process, we learn a lot that have been studied extensively, especially stress-related issues. Give example. They found out that because the dummy gate formation, and they are sitting on a strained buffer, right? You have a strain relief buffer underneath. So this fin is more higher tendency to tilt, okay? Once you tilt, you're dead, right? Device here, transistor here is dead because you cannot have work function coming in and do what they're supposed to do. So this is what they study, and they have to optimize the process so to avoid this gate buckling or a fin tilting issue. So these are because the stress related issue, and it's from the SiGe layer below it. Okay, and it could be so the fin buckling issue can be exacerbated. That's a problem, and then people find out you can solve the problem for sure. Yeah, but it's not as easy as you saw here. Your PR process needs to change. I think that's the bottom line. And what are the other concerns? Oh yeah, there are. SiGe has a low K value. If you look at this one, SiGe This is pure silicon. This is silicon. Germanium content on the x-axis is pure germanium. It's pure silicon. Pure silicon thermal conductivity watts per meter Kelvin is 140. Decent, pretty good. Okay. And then germanium is not that good at 60. Okay, say one half, one third of it. Not too bad. But if you lower, it would quickly drop down to a bell shape, right? It quickly go to 10, right? 9, 10, when you have even 20% germanium. Initially, you think this is an alloy, right? It's an alloy. You should do, say, okay, a straight line, just line up together. It's like an extrapolation, a linear extrapolation. So 20% germanium, I should get like 100. All right, just eyeball it. No, the reality there is a bell shape. It dropped very quickly like a rock. It become 10. In 20% germanium, you lost more than 90% of your conductivity. That's amazing. What makes even worse is that if you make a thin film out of it, oops, okay, it drops even further. So if you got, say, a couple nanometer, right, then you could be 100x off, become 1. And this 1 is like SiO2, all right? So this is how bad it is. A thin film SiGe is acting like a pure insulator now. Okay, so, and you wear, so what's the problem? So it becomes an insulator. Well, if you have any high temperature process, like spike anneal, solid phase epitaxy, regrowth, or laser anneal, very high temperature, okay, that apply in a source and drain, like a spike here, RTA spike, contact for your SPER or your RMG process, laser anneal, your wafer could buckle, okay, your wafer could buckle. And this, of course, it pretty much destroys the process, the wafer itself, right? If you don't take care of it, your wafer buckle, and then your mechanical arm cannot handle it. Something happens, you could crack the wafer, or the uniformity across the wafer is destroyed. Then you have no device, right? The wafer will be scrapped. So you can see that. Is that going to really happen? I'm not sure. Depends how thick your SiGe layer is, right? It's very thin, you're probably okay, right? But it's very thick, that could be a problem, right? Because very, very thin, it becomes SOI. SOI, people did it. SOI process flow is different from the regular FinFET flow. You have to learn from that. We'll discuss that later. So this is the 5 concern I mentioned here, okay? Then, so SiGe has so many problems, so why don't we do SOI? Okay, SOI wafer eliminate most of the aforementioned issue by nature, right? The quality, the quality of silicon is good because using they're bonding 2 wafer together using the highest silicon quality you can buy, right? And that's pretty good wafers. The problem is, of course, you have heat transfer problem, yes, but people have done that, solved that problem to some big extent. And also, it's very costly. It's a couple $100 per wafer, 300, 400, 500, I don't know. It's pretty expensive compared to the regular silicon wafer, which is about less than $100, right? But if you look at the total wafer cost, silicon, TSMC 3 nanometer cost is 25,000 wafer at that dollar per wafer. And you're telling me your new wafer cost $300 to $400. So what's the problem? Well, it is true. It's only about 1% or around 1% impact. But still, every penny counts, right? Yeah, you add the 1% more cost. Is that tolerable? Yes and no, right? And every company, every foundry have their own way of taking this into account. And there's an even bigger problem. What is the problem? It's because silicon uninsulated process flow are still immature, extreme nodes. What's the most mature process flow? 28. Everybody did pretty good job. GlobalFoundries, Samsung, or even TSMC, right? They did a pretty good job at 28 nanometer. Okay. And they work. And what they're doing now, they're trying to extend this to 20 or 18 nanometer now. And nobody has successfully demonstrated SOI on FinFET or on GAA at 10 nanometer now. All right. And then we are talking about SOI pushing, to this flow to 4 nanometer or beyond. And you don't have any HBM experience. That's the key. Nobody, including TSMC, Samsung, Intel, has HBM experience when building their device on an SOI wafer or SOI nanosheet. So it's indeed a very risky move, right? So every idea we put out here, either your establisher, either using SOI or SiGe, they are all a lot of process-related issues that you need to solve. More than I've shown here. I'm just giving you a highlight of the potential problem that I saw from the IMAX flow. Even I can tell a lot of problem here already. All right. And then the TSMC Intel, they are working on that to make it high volume manufacturing ready. And that is not an easy job. And that's the reason TSMC say, oh, okay, I'm gonna put nanosheet first, make it work, the 2 nanometer and N2X, something like that, make it work. And then I will start put this backside power, backside PDN beneath it to make it work. So that approach, I think the very conservative one, I think is the right approach. You have to make your nanosheet work before you go to something else. All right. You don't want to put 2 new things together and you don't know what went wrong. All right. Later you will fail. And that's the mentality TSMC has. I think that's a healthy one. Okay. So my conclusion is that silicon germanium or SOI etched layer, their HBM readiness still has a long way to go. All right. And I think you appreciate that as well when I mention all these problems. And so come back to my title, which etched layer is best for you. I may already decided it's SiGe, TSMC, and Intel. They could choose SiGe or SOI. I don't see other material is good for the etched layer here. Maybe there is. I just don't know. And this is a natural evolution. I think, yeah, either of them had their own advantage and disadvantage, their pros and cons, and it all come out to the process readiness at the end of the day. Especially, you need to have very high yield. Okay, and all right. So thank you very much. I will close my talk on this topic today. Thank you.